Hey everyone, I'm Anuj Harasinghani and I'll be taking you through my work for this course's project. My project is titled Map Elites with Novelty Inspired Mutations. In this project, I've made an adjustment to the default Map Elites algorithm in hopes of getting a variety of behaviors. The default algorithm is described as follows. The user specifies a genotype and n number of behaviors that they find interesting and would like to see the genotype exhibit. Every genotype produced is measured by a fitness function, and an archive keeps track of these genotypes and their fitness values. The archive is an n-dimensional matrix where n are the number of behaviors, and each cell stores a specific fitness value and which corresponds to a specific genotype and its behavior values. For the first few iterations, as specified by the initial iterations, the genotypes are initiated randomly. After these iterations, the archive is accessed and one of the existing genotypes is randomly selected, then randomly mutated to create an offspring. The offspring is also tested through the fitness function, and its fitness and behavior metrics are stored into the archive. Now, I consider the random mutations to be an uninformed way of mutating a genotype, so I thought of adding a distance threshold to the genotypes in the archive, which would govern the mutations. As an example, consider that the algorithm has run up to a certain point of generating some initial genomes and filled up the archive. The algorithm has randomly selected a genome, and given a distance threshold d, it would be required to find k neighbors that are less than or equal to d distance away from g. So the number of genotypes found within this distance would be the k, and the mutation would be proportional to the k that is found. My hypothesis was that this informed way of mutation would result in the archive filling up faster as compared to the default way with random mutations. For my setup, I have applied the default and the modified map elites versions on the humanoid walking problem in Mujoko Pi. The fitness metric for the walking humanoid is the distance it covers in a single run on average. To keep the archive simple, I chose two behavior metrics, one being the step distance and the other being the velocity of the humanoid. The step distance was calculated as the distance between the contact points of the ground with any of the feet. It was ensured that only one foot was being recorded at a time, and the steps could be with the same foot consecutively. The points of contact and the velocity were extracted from within Mujoko at every time step. I chose the archive to be of the size of 25 by 25, giving a total of 625 cells to be filled. The number of iterations for the map elites algorithm was chosen to be 1,000, and the number of initial cells to be filled would be 250. To remove variability as much as possible, I created a bootstrap archive, which is an archive with the initial cells already filled. This bootstrap archive is passed on to each of the algorithms. With an existing bootstrap archive, the algorithms would skip the initializing the genome phase and would only carry out the selection and mutation portion. So I compared the default algorithm with 4 instances of the modified algorithm. Each instance of the modified algorithm had a different distance threshold. All had the same bootstrap archive. I had initially planned to run this setup 5 times to make a better analysis, but due to time constraints, I could only do it once. So here are the results. The Bootstrap archive had only 11 cells filled when it was created, but then when it passed on to the other algorithms, it had the other algorithms made 25, had their cells 25 filled. Unfortunately, the maximum fitness found across all the algorithms is the same, which indicates that the genomes did not really learn how to walk. And they exhibited almost the same behaviors if the cells are staying constant. These are the heat maps which show the distribution of elites in these archives with their fitness scores. The first one here is the Bootstrap archive, which has just 11 elites filled up, while on the right we have the default algorithm with about 25 elites filled up. Interesting to note here that most of these elites are staying close towards the top left corner, which indicates that the step distance and velocity metrics, the behavior metrics, were not that diverse. And in general, the fitness values are also not too great. To conclude, the modified algorithm did not increase the number of cells filled compared to the default algorithm. I think this is because none of the genomes actually learned to walk, so the fitness scores were stagnant and low. There were a few genomes created by each of the algorithms, but they tended to exhibit the same behavior metrics. Also, the cells that were filled up were very much close to each other, so not as much diversity as I was hoping for. Based on the environment and the behavior metrics, map elites can become very iteration hungry. That is, it may require you a lot of iterations to successfully map a majority of the search space and find the best possible solution. There's certainly some issues in the implementation, and my future work would include improving upon these mistakes and having more runs of the algorithms, maybe even on a simpler environment. Here's an example of the human falling flat. That's all from me. Thanks for watching.